Hello guys, sorry, I saw the videos, the lectures, the 14, 15 and 16, and I had 17 already done, but the problem with them, I saw the writing, they're not that good, you can't see the programs, so I'm gonna read all of them from scratch, especially the programs. I'm gonna concentrate on the program, so this will be a good review for you guys. So today we're gonna do some call dump register just to see the output of the registers. It's like the addition and subtraction and increment and decrement, the example we did in I think 14, was it lecture 14 or 13? Anyway, how does what's the template or the body of a MASM program? We're gonna have include airline 32.inc, and then we're gonna have the data, and it's not necessary we have to have data, but I put it just to show how MASM program looks like. So main process, this is the code part, dot code, and main process, this is one part, this is the code part. Now we're in the code part, and we have at the end, we're gonna have end main, yeah, or no, we're gonna have exit, sorry, and main, end process, and end main, and we're gonna write our code in this part here. Do we have data? No, so we can comment this. How can I comment it? With a semicolon that will comment it. And now what we need to do is, I'm gonna give there's an example. You're gonna take the first examples in the lecture, chapter 3. So I'm gonna give it to you guys. It's gonna have like something like this: move, and let's say this is an instruction move, and we're gonna pick EAX, and let's make it 1, 2, 3, and 4, and this is 4 bytes, and then I'm gonna say add to EAX. Doesn't matter, I did the capital on purpose to show you assembly is not case sensitive. And here it's not necessary to put the same size. Less doesn't matter, but more we can't. This is 4 byte, EAX is 4 byte. EAX is here 4 bytes, but this is not 4 byte, this is 2 byte. That's not a problem. It will consider, it will take those as zeros. Those 2 bytes left, so it's not a problem. And let's say increment EAX, and let's decrement AH. You know all what AH is? Remember, EAX is the 32-bit register. We can divide it into AL, which is 1 byte, 8-bit, A low, the rightmost 8 bits, and then we can have A high, which is the second byte, this bit from 18 to 16, and we can do AX, and AX is from, and let's do this AX. AX is from the first 2 bytes, 1 to 16. So we have those. Anything? Okay, let's go back. This is the airline library, and this is considered. That's why they consider this as high-level languages, because makes it much easier. You can see how we use which functions. For example, in this we're gonna use the call dump register, and usually if you want just an output, you only put it at the end here, just one. But I want to put each instruction call dump register so we can see the output. It's like debugging. And here so we have one, we need one more. Okay, so let's see the proc part. I just want you to see all of it. So include, we said it's the library that contains those functions. It contains micros, it contains .code, .data are directives. And what did we say directives are? They're instructions, but they're not part of the instruction set architecture. But they can be added and included, and the compiler recognizes them as instructions, so there's no problem. But they're not they're not an instruction set architecture. That's why they don't call them instructions, they call them directives. Then we have the main process, starting a program, if you remember, like C++ into domain. And now we're moving, we have a move instruction. Move instructions takes 2 operands and it has 5 restrictions. Remember the restrictions, guys. And I'm moving this hexadecimal number, which is 4 byte. Every hexadecimal number is 4 bit. So here's a byte, here's a byte, 1, here's 2, and here's 3, and here's 4. That moves, and here what we did is, and this is a comment, I'm going to put a comment, EAX, we're saying equals 1, 2, 3, and 4. That's what we did here. Now we're calling dump register. Now it's going to show on the output, and then it's going to add to EAX. Well, add to EAX. Sorry. Add to EAX equals EAX plus how much was it? 4,000. And actually what we're doing here, what's EAX? What's this one? This is the 50 million or 5 million, 50 million I think. 50, yeah, 50 million. This is the 50 million, it's going to add it to the 4,000 and save it then in AX. Remember, this has the lowest priority, so it will be done done last. We're called the dump register now, prints the value of each register. Now we increment AX. We're not incrementing EAX. We're incrementing AX, which is the first 2 bytes of it, and I don't think that's going to change anything here, but I just wanted to show you. And the increment instruction take only 1 operand. We have to remember that it can't be a constant operand. And okay, we talked about the instructions. This is a register. This is a call, a function call, calling this procedure. And remember, in assembly they call them procedures, but they're functions. I think you'll find those in your books, so whoever is taking assembly next semester, you'll find it. You'll find a table in chapter 5 or 6, but it's the procedure chapters. Check it. You need to know all of those, and I'll show you in a minute where we can find them also in the keyboard. help. So here we're doing ax equals ax plus 1, and now we're decrementing here equals minus 1. Call the registers, print the registers values, exit with 0, return control to the operating system, end the main process, and end your program. So this is the first, and this is usually, I just want you to know the call dump register. This is the purpose of this. Know those commands that add, increment. We could have added a sub also here, it doesn't matter, but let's save this. And I'm going to save an example, chapter 3, and remember to add the ASM dot assembly and program, because now we're changing program 1 dot ASM. Save it. Sync the code. Just monitor the game. I just was able to do it as a. Well, now we go to tools, and I have how to set those. How to set them. I lecture 13 tells you how to configure TextPad with MASM on Windows. No errors. Everything is good. Let me show you here. Yeah. And now we link it, and we go tools and run. And here's the registers. I don't know, can you see them? Even if we resize, it's not gonna. Anyway, I'll check it. If it wasn't, if you can't see it, I'll do something about it. So the first, how many column registers do we have? 1, 2, and 3, and 4. So we're gonna have 4 outputs. Those are the first 3 lines are for the first one. The second 3 lines are for the second one, third, and here we have what? The 10 is 1, 2, 3, 4. Those 10 registers, and those are 4 flags. What are the 10 registers? Those we took those, and remember those are in chapter 2, slide 16. Whoever is taking MASM next semester, and I've explained them in. I think I've already explained them more than 3 times during those videos. So please, you have to know them. We have 8 general purpose registers, 4 which is EAX, extended accumulator, extended base, EBX, extended counter, ECX, and EDX. Those 4 we can divide into what? AL or BL or CL or DL to 1 byte. If we're using 1 byte, those registers are 32-bit registers, meaning 4 byte. But we can divide them into 1 byte, AL and BL, and A8 for example. The first byte is AL, the second byte is A high. Both of those bytes together are AX. So we can use either AL, A8, whichever one we want, depending on the size of data that we have. And here, if we can see the move instruction, move accumulator 50 million is saved 50 million in the accumulator. Why do I have the 0 flag here? Because the ECX, when I run it, it return this 0, 0, 0. So one of the registers is 0. 0 flag is set. 0 flag is set. This 0 flag is where? In the flag register. In the flag register. We said we had 10 registers. 4, I explained them in a minute. And one is the flag register, 2 dedicated. One of them is the flag register. And the other is the EIP, extended instruction pointer, which is really important, which holds the address of the next instruction to be executed. And then we have the other 4, which is EDI, EDX, and stack pointer and base pointer. And those are usually the ESI and the EDI are usually used for with arrays, strings. Stack pointer is used with the stack, and I'm going to explain stack in detail later when we get to an example on it. So here in the next command we added what? 4,000. So we're going to have 50 million or 5 million, 50 million and 4,000, and those are 0 stay 0. And now we do increment AX. It's going to increment what? The first 2 bytes by 1, which is the 400 those. And then I'm doing decrement AH, which is the first byte, just the first byte. See the result? Oh, I mean the second byte. See, it didn't decrement. We had what? I should have explained it one here, but we had here AX is 4001. This is AX. AL is 01. AH is what? 40. AX is 4001, and AL is 01, and AH is 40, and we want to decrement the AH, which is 40. And remember, those are hexadecimal numbers. So when I try to subtract 1 from the 0, we can't. We borrow 16 because it's hexadecimal. Remember the subtraction of hexadecimal number. That's why everything I gave earlier is really important, guys. Any small detail like that will confuse you. So we have 16 minus 1, it's going to be what? 15, which is F. So we're left with what? And I borrowed 1 from the 4 now is 3. So we have 3801 for what? For AX. And it shows it here. 3F01. And let's see if we can resize it. So I want to try this too. No, come on. See if it. No, it's not going to make a difference. Anyway, let me close this. I need to close it because I was recording one of the lectures earlier, and bang, suddenly the computer froze. It hasn't frozen in a while, and I lost the video. So I don't want that to happen. Got heated, I think I will load it. This is a virtual machine, I have Windows on it. Now we're gonna run it in the low level MASM. We don't use a library in this one, and I'm gonna use the Ubuntu. This is my Ubuntu machine. I'm gonna use what? DOS box, which is an emulator to emulate the DOS kernel. And you can also download this on Windows. To do it, you need to download DOSBox. You need a MASM to download an assembler, MASM, whichever one you want, and you need a debugger. A debugger is really important, and I'm going to show you why is it important in a minute. So here's our DOS. We don't have DOS in Ubuntu, but now we want to emulate DOS, because MASM is what? Micro assembler is for Microsoft. So what we do is first we mount what where our assembler is. So I say mount C, and we'll do home. My assembler is in home, the gate, and my assembler is 8086. Drive C is mounted, so now we go and access drive C. Oops. Hopefully you see the font, guys. It's not. I'm gonna see how I can change the size of this also. You can't stay this way. But I'm gonna check this video how it's going, and then we'll see what we can do. So now, see, we're in 8086. If you type directory, it will show you all the programs. Remember, because I have a full directory, lots of programs, you can do this gate.txt. It will create a file that will have the output of the directory command in a file. So you'll have the name of all those files in a file. Why do I do that? Because I can't see those files and I can't scroll back to them. And let's see the debug. Remember yesterday we couldn't illegal command okay, debug, sorry. Okay, now it showed us. Those are the options for the debugger, but don't worry about it. We're gonna come back to it in a minute, but we need to write a code now. Either you can go, I can go to my Unix machine, or open Git edit and right, but they have an editor here. Here's the editor, and now we're gonna start our code. We start it in a different way because we don't have the F1 library, so we're not gonna start with it. We're gonna start with model small dot model small, and what did we say dot model is? Anything starts with a dot is a directive. A small indicating that, and this is for the memory model, because we're using small programs, or not that memory it's using, so we have other models like flat, large, huge, depending on the size of the program. Model small dot stack. I have to have the stack, give it a size 100, although I'm not using it. Dot data dot code, and we can say here begin colon. We have to put a colon here. Can we change the size of this? Can you see the oops. I'll take it and put it in a gedit file so we can see it in a better way in a minute. So first thing we're gonna start with is move what AX, and move it to, we're gonna move the address at data, the address where the data segment is, where this is. So it saves this in the data segment register. And why didn't I do move DS add data? Why am I doing this? I'm adding an extra step here. I'm moving it first, the address to AX, then I'm moving it from AX to DS. Why is that? Because we can't have immediate. This is an immediate value. It has a number, a constant. I can't have immediate to segment registers. I can't have immediate to EIP. You want to change the flow. Those are the rules of the move instructions. So be careful, guys. We didn't do this in the previous step. That's good. This is, hopefully this is better. If I take it a little bit on the side, I can't move it, and I don't think you can see the whole code. But anyway, so we have and now what we're gonna do is, I don't want to, let's say, move, and this is a 16-bit, so we can't use EAX. I'll show you how to do the EAX later. Let's move to it. Here's 4 bytes, 2 bytes, and then what did we do? Add, let's say AX with 20 text, and let's say we increment H, let's see the difference, and we decrement AL. And here we're gonna need now, this is what do we need, and begin, yeah. But sorry guys, I keep, if you touch the scroll, they keep going up and down. I think of it as a terminal. I always use it as that. But is that enough? Is this enough? Why not? Always have an answer. No, because where's that exit? Remember we had exit, main, end process, and end main. We had 3 things, which is exit 0, return 0. So we need it here, and the exit was part of the Irvine library, so I can't put here exit. It's not going to work. It's not going to take it. We need to program the exit. How do we program it? We're going to use a lot move AH for what? With a system call number, with a number. Let's say with the number 01, which is 1, it's going to be, I think, read from input, meaning a CN, move AH 2 is writing to output, standard output, move AH 09, it's printing a string to standard output, and you get used to them step by step. Don't worry about them now. Just try to know the 01, which is the input, 02 output, 09 string, and most importantly is the 4C H, which is the exit. That's not enough. This is the system call number. I'm saying this is the system. I need to call the kernel, the DOS kernel, and we do that by interrupt, and for 21H. For Windows it's 21H, for MASM, for NASM it's 80 to call the kernel. So I think this finishes our program. We need to save it. And I'm going to save it as program 1.asm. And now what do we do? What do you think now we do? We need to exit the editor, go back to the DOS terminal or kernel, and do what? run the MASM, and what am I gonna give it? Program 1 with a capital letter, program 1.asm. Just leave them in 6 severe errors. What errors do we have? Let's see. Expected instruction or directive in line 1. Dot model. What's dot model? It's a directive. Why didn't like? And I did a dot model. Missing or unreachable CS. Preferably, I always like to fix the first error and then expected instruction or directive. Let's go back to our code, but I'm not gonna go through. Now the mouse is not working, but I'll get it. Even the touch screen now is not working. Come on, DOS, don't do that again. I did it earlier, stopped, and the video was gone. Okay, if I have to open it from here with edit, I'm gonna go do file, open, and we can do program 1. Okay, we have spelling error. Now the mouse is working, so can I open a file here? No, I can't get out of that screen. DOS. So now we do file save and go and run MASM again. File exit, and we do MASM program 1.asm. Enter. 0 warnings, 0 errors. Can I change this up? Okay. Now we need to link it. We did the MASM command, now we link the object file. After we ran the MASM command, an OBD file was created, an object file. So same name as program 1. So I'll have link program 1.asm. Enter. Invalid object model. No. Okay. You're not gonna see it. This is what I'm gonna do. Now the mouse is working because I put link ASM. It's OBD. Linked. Didn't give me any errors. To run it, just put now program 1.execute has been generated after I linked. After I did the MASM, .obd was created. After I did the link, .exe was created. So now we need to run that .exe. We'll do program 1. It will run it, and if you put .exe, it will also run it. It ran it, but did it give me any output? There's no output. We didn't ask for any output. We just did a move, and in the registers, we used the dump registers there, called dump registers to show that output. If you want to program the dump register here without a library, it's gonna take us maybe a whole day to do all that. It's gonna be hard. So the solution is debug. What? Program 1.asm. We open the debugger, do a U and C. This is our code. This is the code we wrote earlier. If you see, those are addresses. This is the segment addresses inside the segment. 1 byte memory. 1, 2, address 1, 2, 3, 4, and those are all the same address. We have a column between them, and remember, we add them. It's called calculating the physical address. We put those under each other. We shift the first one. This is the offset. This is the segment. Offset and segment. Okay. I'll show you how to calculate the physical address. So we have 2E. Do you see this 2E? Here 6D, 6F. What are those? 6.4, 6.5. Those are not addresses. Those are our code, the commands. They're translated to those values. Now we can do T, and it will show us the registers. Debug T, and look, we're still in the debug. When you do the debug, you see those dashes. You can write any command you want. If you do question mark, it will give you what? All the commands that the debug takes. All the commands. I did a T, address value, small t. There is no. What's this? A is an address. C range address. Dump. Okay, we can do a dump here. Register, quit, search, trace, right. Output, load. But how did those are not the debug options. Okay, dash, question mark. Okay, because I don't want those options. Those, they gave me the options for that. But anyway, here's T will give me this. U will give me the code and deassemble it. This is the code, our code in object. This is the values, the binaries. Those are in hexadecimal. That's why we say, if you know hexadecimal, if you know assembly, you can hack the code. Usually this is the object file. This is, if you get this code, you know the values, you can translate it easily back to assembly, and then you got it. You got the code. And we can see the registers here. AX is even 0. It didn't change. And I'm surprised why is that. It didn't take the command. Maybe that's what happened. But you guys, I'll be back. Okay guys, I'm back. I got the code here. But let's see what's happening. AX wasn't changing. Yeah, it didn't change. 0 was 0. Did it use? Oh no. X. Something went wrong. Let's quit. Okay, I'm sorry. Let's quit the debugger and let's do debug. symbol trace T. Okay, no, that's right. Okay, trace is T. That's good. There it says okay, quit. Okay, no. Those are the right ones. So we do do. This is symbol, and we do question mark if you want to see them. Now we want to trace it. T is the first. T again. Did anything change here? Is the doing the deassembled code? We can see the addresses are changed. Do you see it? Come on, mouse. Check the last line from both outputs. The last line says 073F 0102. This is the address, and then it has the 6F. And now we go down. It's 073F and 0103 and 64. So it's running. It's working. Do another trace and see, but AX is not changing. This is what. But there's some instructions that are. Here's AX. Changed. What did it take it? D6C. AX has D6C. Why is that? What did I move to it? Come on, don't do that. Let me quit it so I can show you why is it. This happens because the emulator takes lots of clock cycles from it. So weird stuff are going to happen. But anyway, we moved 5,000, we didn't put 8. So it took it by default as decimal. And it's going to convert it to binary then, and it's going to find the hexadecimal value. So this is the hexadecimal value for the 5,000. Try and check it and you see the answer, and then we can continue on the code. Is it moving? I should have moved it a little bit further. So let's do debug again and program Ramon.exe. Here you can see now it's the cursor's changed. It's this. So we're in the debug. They had a command D. What is it? Dump. Okay, this is a really okay. This is another really. This is the whole code. This is the binary bytes, the bytes. This is the most important for the hacking. B8 is 6B07 0E. Who can tell me where the 5,000 move with the move instruction? I think it's B8. It's byte number 1, 2, 3, 4, 5, 6. Byte 6, and I have after that the 0050. I guess so. D6C. Do we have a D6C in that line? No, so it is it. So this we did. Let's go exit this, and let's exit the DOS. So at least I can use the mouse. And here's the code for the program we just did, which is similar to the one we did in the Irvine library. just so you can play around with it. Look at both and see the differences. See what we can do, what we can add. It's really good. It's nice to know the differences. I think you'll be give you more experience and more understanding of what's going on. Honestly, I felt much better in assembly. Like I felt I understood it after I learned another assembly language. Not the first one. The first one I learned was MIPS on the MASM simulator. So I'm gonna post this both codes, on the description in the lecture. Thank you guys.